Welcome to the audio version of the GOES 3.9 micrometer channel visit session. My name is Dan Lindsay. I'm located here at CIRA in Fort Collins, Colorado. I work for Noah Nesdis. This session was put together by several people, including myself, Dan Bicus, and Jeff Braun here at CIRA, Don Hilger, as well as Scott Bachmeyer up at SIMS. This session has four primary objectives. The first is to review the science behind the 3.9 micron channel. Second is to discuss the many possible applications. We'll look at a number of examples. And then finally, we'll preview what's to come with future sensors. This chart shows the channels available on the current GOES satellites. You can see that we have a couple of channels which differ between GOES East, which is GOES 12, and the Western satellite, which is now GOES 11. But the focus of today's session is actually going to be on channel 2, which is of course centered at 3.9 microns. And throughout the session, I'll be referring to this as either channel 2 or the 3.9 channel, both of which of course mean the same thing. The ground resolution of the 3.9 channel is about 4 kilometers. At the mid-latitudes in the central U.S., the size of that pixel actually turns out to be about 4 by 7 kilometers. And you can see down here where I've given a brief little summary of each channel that channel 2 primarily measures both emitted and reflected radiation during the daytime. And the other channel, which we'll be talking a bit about today, is channel 4, and this is your typical window infrared channel. It measures emitted thermal radiation. Now we'll talk a little bit about the 3.9 band and some of the science behind the reason that it's chosen as a band on the GOES satellites. On the left here, we have the Planck curves for something emitting at 6,000 Kelvin, and this is supposed to represent the sun, and something emitting at 300 Kelvin, and this is supposed to represent approximately the temperature of the Earth's surface. And then, so on the y-axis here is radiance, and on the x-axis is wavelength. And if you center on 3.9 microns, that's the little band which is drawn here, the vertical line in the middle. And then if you actually blow up within the box that I've drawn there, that's the figure you have on the right. Now, if you look closely, you can see that we have 3 curves now for the solar radiation on this. And the 100% represents 100% of the 3.9 radiation being reflected. 50% means 50% reflected, and the 20% means 20% reflected. Typically, the values of reflection are down closer to 20%. So if you look at that curve compared to the emitted curve from the Earth, you can see that both contribute about equally at 3.9 microns. So that means during the day, we have to worry about both reflected radiation as well as the emitted radiation from the Earth's surface. If you prefer to think about this idea in terms of an equation, the radiance at 3.9 microns can be written as 2 components. The first component on the left is the emitted component. It would be the emissivity of the object that's emitting at 3.9 multiplied by the Planck blackbody radiance at 3.9. And then you add to that the reflected component, which is the incoming solar radiation at that wavelength multiplied by the reflectivity. The 3.9 micron channel often has extreme noise on the tops of cold thunderstorms at night, and these plots explain why. On the left here, we have the Planck curve for an object emitting anywhere from about 210 Kelvin or very cold to around 300 Kelvin on the right. And the little lines on the left here indicate the typical noise associated with the instrument itself, or the error associated with the instrument. And if you take that estimate at 300 Kelvin, it's actually quite low. It's only about plus or minus about 0.2 degrees Celsius or Kelvin. But if you go down here to the bottom, you can see at much colder temperatures, just a small error in the radiance results in a very big error in the temperature on the order of maybe 6 degrees Kelvin. And that's why you often have this noise problem. It's basically because this Planck curve becomes quite flat here at very cold temperatures. If you compare that to the curve on the right, this is for the 10.7 channel, you can see that it actually doesn't become flat like that at cold temperatures. It still has a pretty good slope to it. So that means that at the 10.7 channel, there's very little noise at any temperature, even at those quite cold associated with thunderstorms. This image shows an example of the noise that we often encounter with a 3.9 channel at night. So this is just the 3.9 channel as you would view it on AWIPS with a particular color table chosen. And we're looking at some cold thunderstorm tops at 9:45Z. This is when it's still dark, and you can see the speckly nature on the tops of these storms. And this is the noise that I speak of. And for this reason, in general, when you're looking at cold thunderstorm tops at night, it's best to use the 10.7 channel instead of the 3.9 channel. Another issue that you sometimes have to deal with a 3.9 channel is saturation. This occurs whenever, either with GOES 11 or GOES 12, the scene temperatures get really hot. And the time this most often occurs is with fires, although sometimes in the desert southwest during the middle of summer you can get temperatures this hot. Whenever the scene temperature is greater than about maybe 336 Kelvin, then the channel saturates, meaning that even if it got hotter, then you would still be at the top of the brightness scale. Another problem which occurs only with GOES 12 and not with GOES 11 is whenever you get these saturation temperatures, sometimes the scale will actually roll over to cold temperatures. Here's an example. This is looking at a hot fire on the north rim of the Grand Canyon back in the June of 2006. From GOES 11, you can see the fire is really dark. It's giving a temperature of about 330 K. That's on the upper end of the scale here. But from GOES 12, if you look, it's actually giving a temperature of 163 K. And that's because what's happened is we've saturated, and the radiance has switched over here to the very cold numbers, and it causes depending on the color scale, it causes it to go from a black dot to a white dot. You can see that here. Now, it turns out in fire identification, this can sometimes actually be helpful for you because it sort of makes the white dot will flash at you, and it's easier to see than just a black dot, especially if some of the surrounding pixels are pretty hot too. But it's just something to keep in mind, and remember that it typically only occurs with GOES 12 compared to GOES 11. Now we can start talking about some particular products which are available with the GOES 3.9 channel. And we'll start off with a simpler case, and that would be at night. And it's simpler because we can actually ignore the reflected component and focus only on the emitted component in the radiance from the 3.9 channel. So as an example, this is a slide which was pulled from a comment session talking about the 3.9 channel. And on the left here we have a diagram. On the bottom is the 10.7 channel, and on the top is the 3.9 channel. Focus first on the 10.7 channel. It turns out that the emissivity of a water cloud is fairly close to 1.0 at 10.7. So that means that if it's thick enough, then when you have radiation emitted from the surface, just about all of it will be absorbed, and then it will be re-emitted at the temperature of the cloud, in this case 7 Celsius. So the satellite will actually give you a brightness temperature of 7 Celsius. Now at 3.9 channels, oftentimes with these water clouds, the emissivity is a bit lower than 1. And if we assume for this example that it's 0.75, then if we have a 23 Celsius ground and the emissivity is 0.75, even though the cloud is emitting at 7 degrees Celsius, the satellite's going to see a colder temperature of about 1 Celsius. So if you were to take the difference between the 10.7 and the 3.9 channel, you would get a positive number here, and that's because water clouds have a larger emissivity at 10.7 than at 3.9. And this is the basis behind the fog product, which is essentially just the channel difference between 10.7 and 3.9. And I'm going to be talking quite a bit about the fog product or the difference product in today's session. As was stated on the previous slide, the difference between 10.7 and 3.9 channel should be positive for water clouds, and examples of water clouds include fog and stratus. But for some reason in AWIPS, it turns out that the counts are negative. So if you plot up the fog product and actually turn on your sampling and put the cursor over an area of fog like we have here in the Central Valley of California, you'll actually get negative counts, and that's fairly confusing. But it's something to keep in mind, and it's something to understand if you're going to build a color table, which is appropriate for fog, which I'm going to get to here in just a couple of slides. Making use of your enhancement table in AWIPS is extremely important with the 3.9 channel and with the 10.7 minus 3.9 difference product. It can make things much easier to see, and here's an example of what you could do, and this is completely up to you, but I do recommend that you design your own and then save them at your office so that everybody at the office can use them after being trained, of course, on exactly what the colors correspond to. But it turns out in AWIPS that fog typically is going to be between somewhere about minus 20 and minus 5 counts. So if you pull up your little color table thing, what you could do is, one example is you could make everything, all the counts between negative 20 and negative 5, a constant yellow. And if you do that, this is what it looks like. It makes the fog here in the Central Valley of California show up quite well. You do get some noisy pixels in other areas which may or may not be associated with fog or water clouds. But in a loop, you can see that these are blinking, and the fog, the persistent pixels show up really well. Here in the middle, we do have some higher clouds moving over, which actually hides the fog underneath. If you'd prefer to avoid using colors and prefer to use a grayscale in creating your color tables, this is another example of what you could do. What we've done here is notice by using the sampling that basically the highest count in the entire image is about 35, the lowest is about -15. So everything below -15 we've made a constant white, and everything above 35 we've made a constant black, and then we've done a linear stretch between them. And when you do that, it once again makes the fog stand out quite well. Now, in doing this session live, several offices have told me that their default color table for the fog product makes the fog black rather than white. And that's perfectly fine if you prefer that. In that case, you would just reverse everything, and you would make the negative counts black, the positive counts white, and then do the linear stretch that way. And the same result would show up. It would make the black show up against the surrounding white much better. One option you have, if you'd prefer that the difference product actually have some meaning, is the following process. What you can do is go to this website, and it gives you the steps involved in basically altering your AWIPS program to change it from when you sample the difference product. It normally, like I said before, it gives you negative something counts for fog. It actually changes it to brightness temperature, and it gives you the actual positive value, which is what it should be. So in this case, this particular area in California, -10 counts corresponds to a difference of 4.5 Celsius between the 10.7 and the 3.9 band. And again, go to this website, and it gives you the steps involved in configuring your AWIPS. Now we'll show a few examples. We're going to start here with this California example, and again, we're only looking at night right now. And this is just the 10.7 channel, your typical infrared channel, throughout the nighttime hours. And the main thing to note here is the fact that you really can't see a huge difference in the colors and therefore the brightness temperatures between the Central Valley and some of the surrounding areas. The exception, of course, is with the mountaintops. They're colder. But just taking a quick glance at this, it's not really obvious that fog is covering the Central Valley. This loop shows the fog product, or the 10.7 minus 3.9 difference product, with that linear enhancement which I showed a few minutes ago applied, so that the water clouds and the stratus clouds are going to show up as the white colors compared to the surrounding darker colors. And this is the same time period as that last infrared loop which I showed, but the difference product makes the fog show up much, much better. And this is certainly recommended for nighttime fog identification. Notice at the end of the loop you can see the fog dissipating away from the north, and you couldn't see that at all looking from the 10.7 channel. Here's a second example. This is in the eastern U.S. at a much larger view. Again, we're looking at just the 10.7 micron channel loop, and at night once again. And again, just looking at this, it's not completely obvious that there's fog in some areas. Going now to the fog product loop, suddenly we see lots of these light areas which correspond to the foggy areas. You can see here in southern South Dakota, northern Nebraska, western Missouri, northeastern Texas into Arkansas, as well as much of the southeast. These are areas which are certainly candidates for fog. It's often difficult to identify or to differentiate fog from low stratus using just the satellite information alone. So what's recommended is to overlay something like your surface station observations. And when you do that, in this particular case, you can actually see the stations which are reporting fog, say Atlanta here, compared to those which are reporting just cloud cover. In this case, you can see Kansas City is reporting just cloud cover and not fog, with a larger dew point depression compared to, say, Savannah and Atlanta, which have a lower dew point depression and actually fog reported. And if we step through the times, you can see that remains to be the case in Kansas City. And in this case, it looks like the fog actually lifts a little bit in Atlanta, although certainly it's still overcast with stratus clouds. Another application of the difference product is with identifying thunderstorm outflow boundaries. Now, it turns out that occasionally some low clouds are associated with thunderstorm outflow boundaries. And if they are, they tend to be these low water clouds, which the 10.7 minus 3.9 difference product can be used to help identify them at night. In the loop which I'm going to show on the next slide, we're looking here at northeast Colorado. This is the difference product, and we have this large MCS, which is identified by these noisy pixels, which is moving off to the northeast or to the east. And we have some leftover outflow boundaries down here in eastern Colorado. And when we loop this, we'll see them much better. Here is the loop for that case. We'll let it go for just a minute here so you can have a look at it. And you can start to see that some low clouds have formed along a couple of outflow boundaries. There's one which is roughly like this, moving slowly down to the south, and there's another one which looks like it's moving down the front range of Colorado, something like this, with time, and it progresses onward down in this direction. Now, this is important because at night you don't have the utility of the visible channel to see these things, and so it may be important to identify that they exist and to warn your day shift once they come in that some outflow boundaries are sitting out here on the plains, and they may play an important role in convection the following day. Now, it turns out on this particular day there were some tornadoes reported on the eastern plains of Colorado the next day, which may or may not have been associated with these outflow boundaries. Now we complicate matters by starting to talk about the 3.9 channel during the day, and it's more complicated because we now have to include this reflected component, and oftentimes this reflected component is larger than the emitted component and actually dominates the signal that you get from the satellite. Now, the 3.9 reflectivity, which is this R3.9, varies by both cloud and surface type. And this actually aids us in feature identification. For example, if you want to identify snow versus a water cloud or an ice cloud. Now, we can actually calculate the 3.9 reflectivity, or this R value, in AWIPS. But what you can do is use the difference product, once again, the same difference product during the day, and it provides a pretty good approximation for the 3.9 reflectivity. This is another graph pulled from the Comet session on the 3.9 channel, and it's a nice illustration of the way that the 3.9 reflectivity varies with the type of cloud and the size of the cloud particle. So on the y-axis here, we have the single scatter albedo at 3.9, or it's basically that R3.9, which I showed before. And it's drawn here as a function of the particle radius, in other words, the size of the particular particle being sensed, of both an ice cloud and a water cloud, or even for this ice cloud, you could think of snow would also be the case here. The two main things to point out, first of all, is that the green line is larger than the blue line at pretty much all radii here. And that tells us that water clouds have a larger reflectivity at 3.9 than ice clouds. The other thing to notice is that as you get smaller and smaller particles and you go in this direction, the reflectivity of both ice clouds and water clouds increase dramatically. Now, it turns out that most water clouds typically have a smaller radius particles than ice clouds. So the blue area, typical ice cloud particles, this area in green is the typical water cloud particles. And the result is that you typically get a much larger reflectivity with water clouds than you do with snow or with ice clouds. And we're going to use this fact in some of our feature identification examples in the next few slides. Here again is the California example, which we looked at before, except now the sun has come up and we're going to talk about the daytime imagery. You can see, first of all, that the visible channel, which is what we're looking at here, is certainly the best in identifying locations of fog, mainly because of its better resolution, and you can actually see some individual terrain features associated with the fog. But sometimes it doesn't tell you everything, and the reason is that in this case, if you look at the snow here covering the Sierras, and compare that to the brightness of the fog itself and the stratus clouds in the Central Valley, they actually have a pretty similar brightness, basically a similar visible albedo or visible reflectivity. So we really need an additional piece of information in order to differentiate the snow-covered mountains from some of the surrounding valleys which have fog or stratus. Now, granted, if you are working in this area, say in the Sacramento area, then you know exactly where the terrain is located. But in the example I'm going to show in a few minutes, it's not quite so clear-cut. Here's the same California loop as the sun comes up, except now we're looking at that 10.7 minus 3.9 difference product. And now, just to confuse you, what I've done is reverse the color table now, so that we have the negative counts corresponding to the darker colors and the positive counts corresponding to the lighter colors. At the beginning of the loop, you can see this is before the sun has come up. The Central Valley is quite dark, and this is associated with those negative counts with the fog. But what happens as we step along and the sun comes up is suddenly these become very bright. And the reason is because, remember from the graph I showed just a few minutes ago, that the reflectivity at 3.9 of water clouds is very high. So what's happening is we have large reflectivity at 3.9 over the fog and water cloud areas compared to the snow areas, which are much darker. And therefore, these brightness counts go way up, and it allows very easy identification and differentiation between the water clouds and the snow-covered mountains here. Here's a second, more complicated example. Now we're looking at a visible satellite loop over Wyoming and Colorado after a pretty good snowstorm has occurred in the area. This is back around the 1st of November in 2003. First of all, you can see that we have quite a bit of high clouds and mid-level clouds moving off to the northeast in this case. But underneath those clouds, we have some pretty interesting features. First of all, you'll notice that we have bright values in much of the Nebraska Panhandle, at least early on in the loop, and northeast Colorado, as well as up here to the north of the mid-level clouds across much of northern Wyoming and southern Montana. Now, looking at this immediately, it may be a little bit difficult to differentiate the areas of fog and stratus compared to the areas of snow cover because both are bright. So what we can do is, just like before, use that difference product to help us differentiate between the snow and between the fog and the low clouds. Here is that difference product loop which I just described, and you can see if we stop at a certain time and go sort of to the middle of the loop here, that the bright areas in the visible are now dark here up in southern Montana and northern Wyoming, and that tells us that these are likely snow-covered areas. If we look at the area in northeast Colorado and the Nebraska Panhandle, this shows up as bright, and that indicates that we have water clouds in the area because of the high reflectivity at 3.9, and therefore this is likely fog and low stratus as compared to just the snow cover up here. Now, it's possible that some snow cover does exist beneath the stratus and stratus clouds, but it's difficult to identify that from just this image alone. Another comment about the color enhancements in AWIPS. I believe that it's very important not only with a fog product at night, but this difference product during the day when identifying fog and low stratus clouds. And here's the way that I built the color table, which we were looking at a minute ago, is similar to last time. I sampled around the image and found the brightest pixel and noted that it was around 85 counts, and then the darkest pixel, which was around -5 counts. So I made everything below -5 a constant black, and everything above 85 a constant white, and then did a linear stretch in between. And the result is that you get really good contrast between the darker snow-covered areas and the brighter water cloud areas. And I highly recommend that you do something similar to this, either as something saved in your AWIPS or as a custom enhancement that you just do on the fly. Here we have another snow cover example. This is actually some MODIS data provided to me by Scott Bachmeyer, and we're looking at the visible channel of MODIS over the northeast after a pretty big snowstorm. And you can see, first of all, the blue numbers indicate the observed snow depth at each of these locations. And you can see that pretty much all across New York and much of the Northeast, with the exception of the coastal areas, we do have some snow cover. But the brightness in the visible channel varies, for example, down here compared to the north. And the reason for this is that we have more wooded areas up to the north, and so you're seeing more of the reflectivity of the trees rather than the bare ground here further to the south. But what's not obvious from this is if we also have some fog and stratus mixed in. Now, what we can do is fade this over to the 3.9 channel in MODIS. And in this case, the 3.9 channel high reflectivity values are assigned these darker colors, just this particular color table. And you can see suddenly that these areas along the river here show up quite well as being areas of fog and low stratus. And again, going back to the visible image, with the visible image alone, it was very difficult to differentiate the snow from the stratus clouds. Another extremely useful application of the 3.9 channel is for fire detection. Now, the visit program does have an entire fire detection session, which was put together by John Weaver and Dan Bicus, and it is available in audio form, just like this one, on the visit website. I encourage you, if you're interested in this topic, to go there and view it, because it goes into much more detail than I'm going to go here. I'm simply going to show a few slides just to highlight the importance of the 3.9 channel in fire detection. And now, what we're looking at here are a couple of graphs to indicate why the 3.9 channel is better than the 10.7 channel at locating fires. What we're looking at here is on the left is if we assume that we have a surface temperature, a background surface temperature of 300 Kelvin, and we have a fire associated with a 1 pixel, which is about 500 Kelvin, and then the x-axis represents the fraction of that pixel covered by the fire. On the left, it's for 0% all the way up to where it completely covers the entire pixel. And then on the y-axis is the temperature, or the brightness temperature, at both 3.9 and at 10.7. And what you can see is, first of all, if there's no fire, or if the fire is completely covering the pixel, the temperatures are the same. But if the fire covers part of the pixel, say maybe 30%, you get a massive difference between the 3.9 brightness temperature and the 10.7. It turns out that the 3.9 channel is much more sensitive to these subpixel heat sources and would have a much higher brightness temperature. If you were to take the difference between these two curves, that's what's plotted on the right, and it simply shows that this effect, when you look at the difference product, is much more exaggerated when the fire is relatively small compared to the size of the pixel, maybe 30 to 50%, something like that, compared to when it's quite large. Here is a loop. This occurred during the GOES 11 science test back in 2002, and this was over Colorado. You can see we had several very big fires. In the top here is the channel 2 alone, and you can see we do have this rollover problem occurring so that the hot spots suddenly appear cold and turn white. I realize I said before that that doesn't happen with GOES 11, but this was before calibration was corrected during the science test. So this is what it would look like probably if you looked at it with GOES 12 today. Anyway, what you can see is that these fires show up very well in the channel 2 compared to the channel 4. Now the big one here in the middle, this is the Haman fire, and it's so hot that it shows up quite well in channel 4 too. But these other fires, there's 7 or 8 of them in the image here, don't show up very well at all in the 10.7 channel at the bottom, but they show up very well in channel 2. Now, just like with the other products, I do believe it's probably best to look at the difference product when identifying fires, and it will make them show up even better than this. This is a quick preview of hopefully a future product. Right now, I would consider it an experimental product called the Ice Cloud Effective Radius. And this is actually calculated primarily using the 3.9 channel, in particular the reflectivity of the 3.9 channel during the day over cold thunderstorm tops. And it turns out that there's a strong correlation between the 3.9 reflectivity and the size of the ice crystals at the cloud tops. The larger reflectivity corresponds to the smaller effective radius, and this product actually gives you an estimate of that radius. On the curve down here at the bottom, or the color table on the bottom, you can see that the bluer colors indicate the smaller crystals, while the redder colors indicate the larger crystals. And we have thunderstorms occurring here in northeast Texas and Oklahoma, and also some convection and some convective cirrus up here in Missouri. And there's a major difference in the ice size between these two areas. Here in Oklahoma, much smaller crystals compared to those in Missouri. Now, work is currently underway here at CIRA in late 2006 to identify what the dynamics of the thunderstorms that generate these small ice crystals. It's thought that updraft strength plays a role, and therefore we can look at this and say that these storms are probably stronger than the storms up in Missouri. But it's more complicated than that because there's other environmental factors besides just instability which play a role in the cloud top ice crystal size. In summary, what I hope you've learned is that the GOES 3.9 channel has a number of useful applications. I think that the 10.7 minus 3.9 difference product, which you do have available in your AWIPS, enhances some of these features by removing the thermal component. I think that the most useful applications are fog detection, fire detection, and differentiating snow, low clouds, and high clouds. And as I stressed throughout the session, image enhancement is very important. Each office should create both daytime and nighttime custom enhancements and then train the staff on the proper interpretation techniques. So that concludes the audio session of the GOES 3.9 channel. If you have any questions, you feel free to drop me an email. My email address is dan.lindsey, Lindsey, @noaa.gov, and I would be glad to get back to you and hopefully be able to answer your question. Thank you very much.